Starting the video recorder. Okay, can you please tell me on the chat if you are ready to start? Just somebody who writes yes. Okay, very good. Okay, perfect. So, okay, everybody seems to be okay. Just 1 second. I put this window in another place. I need to put the chat on the other screen, otherwise 1 second. Very good. Very good. Now the chat is on the other screen, so I can have a look at it. Okay. And let me go here. Okay, let's start again from my website, and then I click to tutorials of sustainable design of water resource systems. Just 1 second, I check that the video recorder is going forward. Okay, and then let's click again on inductive method for assessing water resources availability. In this page, now I turn into another visualization mode here. Just 1 second, I go back. Assessing, because this is full screen, I like it. So let me go down where we got at the end of the last lecture. We got here, if you remember, we discussed a little bit this Google map, which is an aerial view of a barrage on the river Danube. So now I would like to discuss another example of a barrage, a river barrage for water withdrawal. Sorry, this is not for water withdrawal. This is for hydropower production. I think you may have seen already this example, which is the hydropower plant of Isola Serafini on the Po River with Professor Castellarin. I'm not spending much time. Basically, they use a meander of the Po River to produce hydropower, because you see the map of the meander here. The meander is quite long, and they had the idea of cutting the meander, so getting a much shorter channel connecting upstream the meander with the downstream meander. And in this way, they, by putting a barrage on the cut channel, they are able to use the difference in elevation between upstream and downstream the meander to produce hydropower. And what is interesting here, it's not only the idea. Keep in mind that this is the only barrage that is located over the Po River. Yeah, you can see the screen because I forgot to, sorry. I forgot to share it. Just 1 second. No, you're not the only one, I think. Okay, now you should see. 1 second. One second, because I wanna make sure that I share the correct screen. Okay, good. Now you should see it. 1 second, I move this window on the other screen, otherwise. Good. Chat. Perfect. Now you should see the screen. Okay, if you still don't see it, write on the chat, but I am pretty sure that you can see it. As I said, you can see the map of the meander over the Po River here. And be careful, the upstream meander is on the left, downstream meander is on the right. And you see that upstream there are two barrages, one on at the beginning of the meander, on the natural course of the Po River, and the other one is the barrage of the hydropower plant. It is on the cut channel, at the beginning of the cut channel. By using these two barrages, they can regulate the flow along the meander and the flow along the cut channel. Of course, they would like to maximize the flow along the cut channel, but on the other hand, they have to keep a minimum flow on the meander in order to preserve the local environment and the ecosystem of the river. What is interesting to see is the flow duration curve of here you can see some pictures and some technical details of the hydropower plant. But what is interesting to see, as I said, it's the flow duration curve. You can see here in black thin line the flow duration curve of the river stream flow unimpacted. Again, it's the black thin line. With the black thick line, you can see the flow duration curve of the flow that is used for producing hydropower. So you see that the hydropower plant is designed for river flow of about 1,000 cubic meters per second, which corresponds to a duration which may be some more than 60 days, but not much more. Probably it's something like 3 months. And it is also, you can see in a different scale in blue the upstream water level. It's a different scale because on the vertical axis here you can see that we have two variables that are displayed: the river flow for the flow duration curves and the water level. So the upstream water level is in blue. Of course, the scale of river flow and the water level is different. And the downstream water level is again in blue. It's the lower curve. So you see that there is a difference between upstream water level and downstream water level, a difference in altitude that can be used to produce hydropower. And you see in purple the available head. The purple curve is the available head. Available head is nothing else than the difference in elevation between the upstream water level and downstream water level. It means that for the higher flows, you have a lower head. Why is that? Because with the higher flows, you have a water level in the river that is higher downstream. Upstream, the water level is kept constant because they use the barrages to regulate the river flow in order to keep the upstream water level constant. But downstream, there is of course the river flow that it's corresponding to a natural situation, because keep in mind that they cannot store much water into the system. So basically downstream they have the natural flow, and therefore for decreasing river flow they have a downstream water level that is also decreasing, which means that again for high flows there is a lot of water to be turbined, but still there is not much head. Keep in mind that the energy production, so the power that is taken by an hydropower plant, is proportional to the head and the river flow. So in order to get a lot of energy, in principle, we need much river flow and much head. So if we look at the power duration curve, which is the duration curve of the produced energy, it's not very high for high flows, because it's true that we have a lot of flow to turbine, but we don't have a high head. For increasing duration, we have an increase of the produced power because the head is increasing. And then for again increasing duration, for the longest durations, we have a decrease in the power that is produced because the flow is decreasing. So the head is increasing, but the flow is decreasing. It is just a coincidence that the max of the power duration curve is placed in the same duration than the design flow of the turbines. So the duration of 1000 cubic meters per second is just a coincidence that it's the same than the duration of the max of the power duration curve. Of course, we expect that the max of the power duration curve is around that duration, but not precisely the same. Okay, and then this is, I think, a nice example of how the flow duration curve can be used to estimate water resources availability, and not only that, but also to estimate the benefit that we can draw from the flow duration curve. What is the available head, Matteo asks. Available head is the head in a power duration in hydropower plant. It's defined as the difference in elevation between the upstream level of water and the downstream level. So if you put a turbine to produce hydropower, the turbine takes water from upstream and releases water downstream. Roughly speaking, the difference in elevation between upstream water and downstream water is the head. I said roughly speaking because actually the correct definition of head depends on the type of turbine. In this case, it is a turbine for which indeed the definition that applies to head is what I said. Difference in elevation between upstream and downstream water. I hope it is clear. And of course, as I said, given that upstream we can keep the water level constant, downstream the water level is decreasing for decreasing river flow, and therefore the head increases. Okay, now, as I said, this is a useful example, and this kind of graphical representation, as I said, is much powerful in order to convey communication to users. Now, I think that we can close here the topic of inductive assessment of surface water availability. Basically, we discussed the flow duration curve, two methods for estimating it, and also the way in which it can be used to assess uncertainty by using the second method of estimation, which means splitting the data in years. We also made an exercise. Keep in mind that the flow duration curve is a classical question that I ask at the exam, and usually I ask the student to tell me about the two methods for estimation, what are advantages and disadvantages of each one. And as I said, the first method has an higher resolution, the second method allows estimation of uncertainty. This is basically what I'm asking. It's an important topic, and it's important in any design of water resource systems that are fed by surface water resources. Actually, these systems that are fed by surface water resources are typically mountain water supply systems. When we get downstream in the flat areas, the availability of surface water resources is generally lower. The reason is that, of course, you have less rain and than in mountains, and also the use of water as you get downstream increases. It increases the use for irrigation and also for civil use. And therefore, you know, this kind of water supply, surface water, is usually more typical for mountain areas. I look a question on the chat. I did not understand one thing about the max of the power duration curve. Did you say it is just a coincidence that the max is at the corner of a usual discharge, or was that planned exactly like that? I said that it's a coincidence because it depends on the progress of the curve of the available head. For sure, when you get to the duration in this graph of 1000 cubic meters per second and you go beyond that, you get a decrease of the available flow downstream and also upstream. You get a decrease of flow. So, but on the other end, you see that you get a higher head. So let's suppose that the head increases a lot at that point. To compensate for the decrease in flow, you may still get an increase of the power duration curve, because if the flow in the flow duration curve decreases slightly and the head increases a lot, you get a compensation. And it depends on the geometry of the river and the shape of the flow duration curve. I'm not sure I was clear, but if you think that the curve of the available head in this graph increases less than the flow duration curve decreases, it's a different scale, but still we can get from here that probably the decrease in flow is higher than the increase in head. Given that it's a linear relationship, I said it is proportional, linearly proportional. The energy is linearly proportional to flow and head. If you have a flow that is decreasing much more than the head is increasing, you get a decrease in power. But if the available head increases more than the flow duration curve is decreasing, you may still get an increase in power beyond the duration of 1000 cubic meters per second. So for this reason, I said I am expecting the max of the power duration curve around the duration of 1000 cubic meters per second, but not precisely there. It depends on the case study. Maybe that here they are coincident, but this is generally not always true. Okay, as I said, we in the flat areas, downstream areas, usually we get shortages of surface water resources, especially during the dry season, because as I said, surface water resources react very quickly to precipitation, and therefore during the dry season, rapidly surface rivers get dry. So in the flat areas, like for instance the Emilia-Romagna region here, usually during the dry season we rely on groundwater. Groundwater is, for the flat areas of the planet, an important resource, an important water resource. And therefore, it's also important for the sustainable design of water resource systems to understand, to assess groundwater resources availability. This is a challenge. It's much more complicated to assess the availability of groundwater resources with respect to surface resources. Why is that? For a very simple reason. Surface resources, you can observe them, you can see them, you can look at a river, you can measure the river flow with a relatively small uncertainty. When you go to groundwater resources, it's something that is more difficult to monitor because you don't see it. Also, it is highly heterogeneous and widespread in space. A river is very concentrated. A river is there. groundwater resources are below the whole flat area that you are considering. The groundwater body is much extended in space and it's heterogeneous. You can understand that even if flat areas are more homogeneous in terms of shape, in terms of morphology, in terms of soil, they are more homogeneous than mountain areas for obvious reasons, because they are typically alluvial areas. Even if they are more homogeneous, they are still heterogeneous. And for this reason, it is not easy to monitor groundwater resources. And this is what I want to briefly mention now by again subdividing between inductive assessment and deductive assessment. And let's focus first on inductive assessment. Inductive assessment of groundwater availability. I have a picture here of, and I want to visualize it, which briefly explains how aquifers work. Before moving forward, what is an aquifer, first of all? And there is a link here to a Wikipedia page. Let's see if it works. Yes. And let's see what is written here. An aquifer is an underground layer of water bearing permeable rock, rock fractures, or unconsolidated materials like gravel, sand, or silt. So it's an underground water body. I would like to define it in this way. It's an underground water body which is contained into a layer of water-bearing material. And you see the figure that I'm using on my website. I go back to my website now, because this is a typical representation of an aquifer. And I just would like to focus on it with you in order to understand how aquifers work. First of all, the aquifer is fed by infiltration. Infiltration may come from the uplands, from the mountains, meaning that rainfall may directly infiltrate into the soil. Infiltration may come from river and lakes. Infiltration is just a flow of water from the surface to the underground. And then in this picture you see that the groundwater body is feeding the stream, the river. But there might be cases in which it is the stream, the river, that is feeding the groundwater body, depending also on the season. So this infiltrated water gets stored into the soil, provided the soil is able to store it. And the capability of a soil to store water depends on porosity. Everything is described on the web page, so don't worry about what I'm saying about these definitions. Depends on porosity. What is porosity? Porosity, as you may already know, of a material is defined as the volume of voids divided by the total volume of the material. These voids can be filled by water. So the higher the porosity, the higher the potential water storage. But also the capability to store water depends on permeability, which is the capability of water to move into the material and to occupy the voids, which means that voids must be connected. If the voids are not connected, then of course they cannot be reached by water. So porosity by itself is not enough. We need porosity and permeability. On the other hand, a media, a material may be permeable, but if it has low porosity, it cannot store much water. So it's the combination between porosity and permeability that makes the soil able to store water. And both porosity and permeability can vary in space, which makes the aquifer heterogeneous. And in order to understand how much water is there, and therefore how much water we can take, we need to estimate the spatial variability of both porosity and permeability. So you understand, it's complicated. Okay, now let's make an important difference between two categories of aquifers, which are depicted here: the unconfined aquifer and the confined aquifer. As I said, the soil is heterogeneous. It often happens that you have layers that are impermeable into the soil, like the dark blue layer that you can see in this figure. Which means that if water is able to reach the soil below the impermeable layer, water is confined. You may wonder, how can water reach the confined aquifer? There is an impermeable layer here. Water can get there if it travels underground. In this figure, it seems not possible, but actually, if you look in the third dimension of this graph, there might be some travel path from which the infiltrated water can go in the underground. And I show you another picture. Let me see if I can find another picture on the web to show you. Just 1 second, give me 1 minute. And let me search for confined aquifer. Yes, I think, let me see here. Yes, this is perfect. Just 1 second, I see if I can increase this. Okay, let's wait for a while so you get the figure. Here it is. So if you look at the lower aquifer, the lower blue band, it is not focused. The focus is bad, but I think you can get it. You can see, if you look on the left, where water can come from. It comes from infiltration in the left of the picture. Infiltration in permeable soil, in the permeable part between the two impermeable layers, that is emerging upstream. So you have the permeable layer where the lower aquifer is stored, that is emerging in the uplands on the left, and from there it can get water from infiltration. And then water goes down, gets trapped into the confined aquifer. I go back now to the previous figure. So what's the difference between the two aquifers? First of all, the confined aquifer is more protected because the impermeable layer acts as a protection. The unconfined aquifer has the upper part that is in contact with the atmosphere. Even if it's underground, the upper part of the aquifer is in contact with air that is getting into the soil, but still air, which means that the unconfined aquifer has a relative pressure of 0 in its upper part. It is atmospheric pressure. And therefore, if you want to get this water from the underground, we have to pump it because it doesn't spontaneously climb up to the soil terrain level. Spontaneously, it doesn't climb up because it's atmospheric pressure in correspondence of the upper aquifer. Conversely, the confined aquifer is under pressure. If we dig a well, which means what in Italian we call a pozzo, a well. If we dig a well into the impermeable layer down to the confined aquifer, that water is in pressure. It may climb up to the terrain level without pumping spontaneously. Let me go back to the other figure with the poor focus. You see that if you look at the first, let's wait for the figure, okay. If you look at the first well on the left, you see that water is springing at the terrain level spontaneously. If you look at the last but one well on the right, you see that water is not climbing out spontaneously. Also, if you look at the last one on the right, you see that even if it's into a confined aquifer, water doesn't spring out. Why is that? Because, of course, the level of the terrain is higher with respect to the well on the left, and therefore water cannot climb up to the terrain level. Water can climb up to the level of the water on the left that you see, up to the level, to the blue level on the left, which is decreased a little bit because you have a decrease of power as water travels downstream along the aquifer, a decrease of energy. So what is the important message that I want to give you? We can distinguishing the aquifers in two main categories, confined ones and not confined ones. The not confined one is also called phreatic aquifer, and it needs to be pumped, the water, in order to be used because it's underground. Water is underground at the atmospheric pressure. This aquifer, phreatic or unconfined, is vulnerable to pollution and usually placed at a higher level with respect to confined aquifers. Fine. Confined aquifers, also called artesian aquifers, are under pressures, are more protected with respect to contamination. They can climb up along wells and can, in some cases, deliver water without pumping. You have to have clear this difference. As I said, they are more protected, so usually water is has a higher value in confined aquifers. It is typical when you drill a well. When you drill a well, it's typical that you, in a flat region like the Emilia-Romagna region, you first find a phreatic aquifer, and then if you go down drilling, you find an impermeable layer, and you may find a confined aquifer. And then if you drill down again, you may find another impermeable layer, and then after that, you may find another confined aquifer. For instance, I live in Reggio Emilia. We know that we have a phreatic aquifer, unconfined, at a depth which is about 15 meters. And then we know that there is an impermeable layer, which is at the depth of about 70 meters. And then there is a confined aquifer below that, at a depth of about 80 meters. Then we know that there is another another confined aquifer at a depth of about 250 meters. So there are layers of aquifers that we may find. Let me go back to my website and let me go down then. There is a legend and which doesn't say anything more. I think it is interesting for you to look at this video, which is linked here. It is excellent. It lasts about 7 minutes, and it is a nice explanation of how aquifers work. And it emphasizes the difference between porosity and permeability. And I think it is a nice explanation. It is a kind of dissemination material. It is not technical, but still it is I think it is meaningful. So, as I said, it is a challenge for us to understand how these aquifers work. And when we talk about inductive assessment, there is one way that is traditionally followed to monitor aquifers, which is monitoring the water level in wells placed in unconfined or confined aquifers. And typically we drill these wells because we need to take water. And then as we take water, we monitor the water level. The water level is an indication of the aquifer pressure energy. And also it's an excellent indication of how the aquifer reacts to pumping, to water withdrawal. And what is done usually is, besides monitoring how they react to withdrawal, we also aim to see how they react to pumping tests. Pumping tests means that we typically make a stress test. We try to withdraw a lot of water from the well, and then we see how long it does take to recharge. And the longer it takes to get back to the previous situation, the lesser we can rely on this well, which means also the aquifer, for giving a lot of water, because of course we can take a lot of water from a well if the recharge is quick, if the replenishment is quick. If the recharge is very slow, it means that either the aquifer has a reduced permeability or a reduced porosity, which means that in any case we cannot take much water from there. This is a kind of assessment that, as I said, is usually carried out. There is to say that it doesn't provide a final reply to the question, how much water is there, how much water I can use. Because, you know, aquifers, as I said, are quite complicated, and it may happen that they take tens of years or hundreds of years to recharge. And we may not notice that at the first instance, because even if we make a stress test, if the aquifer has a large volume, it is much extended, the recharge may look quick at the expense of the same aquifer, but actually the real recharge coming from the mountains, from the rivers, may take a long time. So the aquifer may take a long time to be depleted. So we may pump water for years without noting a significant decrease in water level. But then, once the aquifer is depleted, then it may take hundreds of years to recharge. So it is still an open question how to reliably estimate how much water is there and how much water we can use. Usually for this task we use deductive assessment, and we will speak about this later on. On the other hand, these groundwater models are affected by a relevant uncertainty, and so it's still a challenging research question, how much water we can use safely in a sustainable way. This is strictly related to sustainability, meaning that, we have to understand whether our withdrawal is sustainable in the long term. It may be sustainable, it may look sustainable in the short term, because as I said, if the aquifer is extended, it may be that we don't see significant decreases in water level, even for large withdrawals, but then these decreases can take hundreds of years to be compensated. So it's still a challenging research question. How to effectively model groundwater resources? If for sure we need to characterize the heterogeneity of the aquifer, and therefore we need a lot of inspections, a lot of wells in order to fully characterize the aquifer. This is possible at the small scale. It's not possible, of course, for very large scales. So it is something that indeed is challenging, and this means that as much as it is possible, we usually prefer to use surface water resources, which are more easily replenished, and also they cost less in general, because from the aquifers many times we need to pump water. Even if they are confined, very frequently we are in the situation where we still need to pump to bring water to the terrain level, and therefore for this combination of reasons, cost and easier monitoring, usually it is safer and more sustainable to use surface water as much as possible. On the other hand, groundwater is a very important resource in cases of droughts. In cases of droughts, especially, they are not so frequent. Extreme droughts are not so frequent, and therefore we can take the luxury of using groundwater, even in a way that may be not sustainable with a regular withdrawal, but it is sustainable if it is taken infrequently, because we still give time to the aquifer to recharge. So it's an important resource that needs to be used with some care, with some rigorous analysis, and the research is still working on that in order to gain an improved characterization of the world's aquifers, because we need to work at a very large spatial scale. On the other hand, it's impossible to characterize heterogeneity when you work at very large spatial scale. So it's, as I said, it's a fascinating research challenge, and we will discuss about groundwater models later. Very good. So let me go down in the page. I think that there is one thing, a couple of things that I want to mention before closing this part. And one further means to inspect groundwater dynamics is to estimate groundwater age through isotopes. It's mentioned here. For instance, by analyzing the carbon-14 content of the water that we get from the very deep aquifers, we can estimate water age by relating also the isotope composition of groundwater with the isotope composition of rainfall, for which we have long historic information that is taken from ice carrots, for instance. And therefore, the analysis of isotopes is frequently used in order to try to estimate the age of groundwater. Still, it doesn't give a final answer, because the fact that an aquifer has very old water, it doesn't mean that it takes long to recharge. It may just mean that water is stored there since a long time because nobody used it, but still maybe that the recharge it doesn't take as much time as water age. So even if we are using a water that is 300 years old, it doesn't mean that the aquifer will take 300 years to recharge, but still it's a useful indication. And another important progress that has been recently done in monitoring is the assessment of groundwater resources through gravity measurements. Because when you have a huge amount of groundwater that is stored in a given location, gravity increases at the same location. Increases because of the concentration of mass into the soil due to the concentration of water. And therefore, by measuring changes in gravity, local changes in gravity, we can estimate changes in groundwater storage. This is a nice opportunity because now we can estimate changes in gravity through satellite missions. And in particular, there is the NASA's and ASA GRACE mission. You see a link here in my webpage. I'm clicking on the link now. I still don't understand why it's impossible to see the mouse in Teams, but okay. And the link is here. I'm selecting it. Let me see. I'm checking on the phone whether it is indeed highlighted when I make a selection. It seems not, which is something I still don't understand. Because I make selections on my screen and it doesn't get selected on yours. Oh, no, now it gets selected. Okay, it's only a bit late. So if you click on the link here that I just selected and you wait some time, it is useful if I look at the phone because I can get when it is visualized in remote. It's still not visible in my phone. Okay, now it is. There is a description of the GRACE mission, and here there is an interesting figure of gravity anomaly. And if you give some time to it to get visualized, this is an interesting figure of gravity anomaly. Gravity difference, and by looking at again at the differences in gravity, we can estimate the amount of groundwater that is being withdrawn in the various and different parts of the world. Now I'm closing this picture. This is an important information. Still, it doesn't tell us how much water is there. So it's not a final answer, but still it's something that is indeed very relevant. Okay, waiting for the web page to be displayed. Let me have a look at the chat because I forgot to have a look at it. 1 second. Here it is. Okay. So there is a question, are the permeable layers variable just spatially or also in time? Now, usually, you know, in a phreatic aquifer, which is confined only below, you have changes in space of the medium, and then you may have changes in time of the water content and water level. But the medium, in general, let me say, the medium usually doesn't change in time, unless there are earthquakes or something like that. So the answer is the permeable layers just vary in space, not in time. As I said, unless there are events like earthquakes, or when you dig a well, of course, you make an hole in the permeable layer, so in the impermeable layer, so you have a change in time as well. But in general, while the water content of the aquifer changes in time and the water level changes in time, the medium doesn't change in time. Okay. Now, this lecture is finished, so I can go back to the list, and then once it appears, we can click on the next one, which is on a similar topic. I'm still waiting for the previous page to appear. It is there, and it's, as I said, on a similar topic, but it's deductive methods, not inductive. the difference, I already clarified what's the difference. The difference is that with deductive methods, you use a model. So usually deductive methods are subjected to more uncertainty, and therefore we typically use them when there are no data. There is no way to use inductive methods, no data or few data only, and to compensate for the lack of data, we typically use a mathematical model. I think to make an example, it's better if we click on this web page, deductive methods, and let's wait for the page to appear. You see that the page starts by talking about rainfall runoff modeling. Indeed, if we refer to surface water, the most used deductive method is rainfall runoff modeling, and let me explain why. We need to assess water resources availability. For surface water, this means assessing river flow. As I said, the easier solution is to use data. And if we don't have data, there are other solutions that can be used. And one possible solution is to use rainfall data to reconstruct the river flow through a model, a mathematical model that is called rainfall runoff model. Now, why is this solution attractive? Because you may say that if we don't have river flow data, why should we have rainfall data? The answer is very simple. Measuring rainfall is much easier than measuring river flow. So we are indeed very frequently in the situation when rainfall data are available and river flow data are not. Rainfall data are more easily available because, as I said, you can measure rainfall by simply putting a tank outside and measuring the water depth that is collected into the tank every day. This is already a measurement of rainfall, and actually the density of rainfall measuring station is much higher than the density of river flow measurement stations. If you look at the collection of data that refer to the Italian lands, and these data are collected by the Regional Agency for Environmental Protection. You can also regional agencies, because in Italy we have 20 regions for environmental protection, and usually these data are made available online, at least the list of the stations. If you look at the data, you will see that the density of rainfall data is much higher than the density of river flow data. And this is understandable if one considers the easy access to rainfall data, the easier measurement of rainfall data. And therefore, it follows that rainfall runoff models are more attractive. Rainfall runoff model refer to a catchment. What is the catchment? Remember, we remain interested in estimating the river flow data to a given location. Typically, it's the location where we want to take water. And this location is a location along a river. Okay, so we focus on a river cross section, which we already defined, and we focus on the area that contributes to the river flow to that cross river section. And then we focus on the catchment. We already defined the catchment. It's the portion, it's the geographical area which only contributes to the river flow at a given river cross section. And we already defined it. Again, it's the portion of the geographical area that only contributes to the river flow to a given river cross-section. And therefore, by knowing the rainfall that falls over the catchment, we may try to reconstruct the river flow. Rainfall runoff modeling, it's a very old discipline. The first who realized that rainfall was connected to river flow was an Italian priest. And in the past, this was not immediately understood. And the Italian priest realized it around 1650, 1600. Before then, it was not immediately understood that rivers were fed by rainfall. And you may find this consideration stupid, like why didn't people understood why didn't they understood that indeed river flow comes from rainfall? The reason why they didn't immediately understand that was that communication was much reduced with respect to today, and especially long rivers, sometimes people get flooded without any rainfall. Like the ancient Romans, they couldn't know that the Tiber River experienced an extreme rainfall upstream. Sometimes they got flooded without any rainfall, and also along the Po River it was the same. So this led to the conclusion that water in the rivers may come from the underground, may come from groundwater. It was only around 1600, as I said, that humans understood that there is a direct connection between rainfall over the catchment and river flow. And then it was in 1850 that Irish engineer Mulvaney developed the first rainfall runoff model. And this first rainfall runoff model is the rational formula. We are not discussing much the rational formula because the rational formula is not used typically for water resources assessment. It is used for estimating the peak river flow. So it is used for flood design, for flood protection, for civil protection, but not for, typically not for water resources assessment. So we are not discussing much it, but I really would like that you know the structure of this formula. And there is a link here, which I am highlighting. It is a link, and therefore you can see easily where it is. And let me click on it and wait to see the resulting web page. This is a web page which is dealing with the estimation of design peak river flow and flood hydrograph. Forget about the error that is given by this website, which is a mirror. I need to correct it, but I didn't have time so far. So this web page, if you scroll down, it provides a quick treatment of the rational formula, but you have to scroll down for a while. I am scrolling down. Here it is. Rational formula. Let me expand the font. It is now appearing. Just wait for a while. Here we are. Perfect. So, please read these few lines and keep in mind the structure of the rational formula. I may ask it at the exam. It gives an estimate of the peak flow Q for a catchment area A, depending on a forcing given by rainfall intensity I and a coefficient, which is called runoff coefficient, which we indicate here with the symbol C. It is also called, in order to better remember it, the CIA formula. C, again, is the reduction coefficient. I is rainfall intensity. A is catchment area. It is a very simple formula. It says that whatever it rains over the catchment area A, we find it in the form of river flow at the closure of the catchment in a reduced amount. Reduction is given by infiltration, it's given by evapotranspiration, and the reduction is estimated through a reduction coefficient C. Very good. Now, this is a very simple formula, which is nothing else than a mass balance equation. As I said, whatever it rains, whatever the amount of water that rains over the catchment, is simply transformed into river flow by applying a reduction coefficient. As I said, this is not typically applied for water resources assessment because it doesn't give an idea of the temporal variation of Q. You see that there is no time index there. In water resources assessment, we need to quantify water resources, the progress of water resources in time. The rational formula doesn't give you that. It just refers to a given rainfall intensity, which is assumed to be independent of time. Basically, you refer to a design event, and basing on that design event, it gives an estimate of the resulting river flow. I just would like that you know it. If you scroll down, there are the assumptions conditioning the rational formula here. I don't need, I'm not asking this assumption at the exam. I just kindly ask you to have a read, but it's not necessary that you study them. And I just would like that you remember how the rational formula is expressed, which is here. Q is equal to CIA. I'm waiting for the screen to be displayed again on the rational formula. Okay, I think we can close this window. And then let's turn into another example of a rainfall runoff model. This is more elaborated. It was proposed, I think it was proposed around the beginning of the 20th century. I'm not sure about the date, but it is for sure an old model. It is called the linear reservoir. And the linear reservoir, alongside with another rainfall runoff model, which we don't discuss, which is called the time area method, it's linked here. We will not discuss this latter model. The linear reservoir, as I said, together with the time area method, is widely used to assess water resources. It's a rainfall runoff model that is widely used for water resources assessment. And the linear reservoir assimilates the catchment to a reservoir, which is fine. I mean, the catchment indeed acts as a reservoir for surface water and groundwater. Some surface water is stored into the catchment, indeed, has volume of water that is flowing into the rivers, in lakes, etc. Some groundwater is also stored into the catchment. And therefore, we can assimilate the catchment to a reservoir. This is a conceptual scheme. To this reservoir, we can apply the conservation of mass. Remember that in any problem related to fluid mechanics, mass balance and energy balance apply. Therefore, water resources assessment is indeed a fluid mechanics problem. If we want to model it, if we want to model water flow, it's precisely a problem of fluid mechanics. So you can rely on mass balance, conservation of water, and energy balance, in particular if you want to describe how water flows. Good. So we can apply mass balance to this reservoir. And let's have a look. I am increasing, but the size of, if I increase the font, the size of the equation doesn't increase. Let me see if I can, yeah. I can increase it in this way. This is the mass balance equation for the reservoir. Let me explain the meaning of the symbols. W is water storage into the catchment. Overall storage, surface water, groundwater, that's fine, all together. So W is water storage. It depends on time. Okay, so you see that this model is describing time dependence. There is no spatial dependence. Why is that? Because the space is fixed. It's the catchment. And we describe then W, water storage, for the whole catchment. So given that it's fixed, we drop it. Okay? The change in storage, so the variation of WT along time, so the derivative, the total derivative, because we have only one independent variable, it's time. So the derivative of W with respect to time is a total derivative. The derivative of W with respect to time on the left-hand side is equivalent to, look at the right-hand side, precipitation over the catchment minus river flow QT at the catchment closure at the considered cross river section. Okay, so even for precipitation PT and river flow QT, there is no dependence on space because space is fixed. Precipitation refers to the catchment, river flow refers to the closure, the considered river cross section. Given that precipitation refers to the catchment, it is implicit here that we have to give an average precipitation over the catchment. The catchment is spatially extended. Precipitation, like soil, is heterogeneous in space. It's changing from location to location, and especially in the mountains and during the summer for thunderstorms, it changes a lot. It's highly heterogeneous. We have to give an average value over the catchment, which is not easy. I know that. It's not easy because you need several measurements and to compute an average. But we will find a way to compute an average or to approximate it. So let's forget about this problem for now. This is the mass balance equation in which you have one known variable, precipitation, and two unknowns, storage and river flow. So we need a second equation in order to solve this. What could the second equation be? Okay, I just said one important thing. I make a premise before I go forward. You understand that we got into a technical topic, a topic that is, I would like to say, it's an engineering topic. So I need your attention. During my lectures, I try to make a mix between technical topics and descriptive topics. So far, my lectures were a mix. We got into a first technical topic, which was the estimation of the flow duration curve. Now we are getting into another technical topic, so I need your attention on that. And I think it is the way in which I'm treating rainfall runoff modeling and mathematical models in water resources assessment is based on highlighting the physical analogy of mathematics with reality. And I really think that this is important. You are an engineer, so you are not a fan of mathematics by itself. You are not a fan, you are not interested in mathematics because of mathematics itself. You are interested in mathematics because it allows you to solve a real-world problem. So it is extremely important that you continuously see the connection between any equation that we use with nature, with the natural process that you are trying to describe. And I will try to continuously emphasize this connection. It is helpful for you because it's easier to learn. If you can associate a relationship, a math relationship with something real, it's easier to learn. And it's also very important for you because a good engineer is precisely able to continuously see the connection between a model, between the math, and the real world. So in this case, what you see on the screen, it's simply a mass balance equation. There is a volume of water that is getting into the catchment in the form of rainfall, and there is a volume of water that is going out from the catchment in the form of river flow, and then the difference is just the change in storage, nothing else. And I'm using rainfall as input variable, so I call the input variable very often rainfall. It would be more rigorous to call it precipitation because it may be also snow, it may be fog. Water can come into over the ground also in the form of fog. Rainfall, of course, is dominating in our climate, but try to have a look at the generality of the problem. So precipitation may also include other forms in which water is delivered to the ground. So my previous question, before I made my premise, was I need a second equation. What kind of equation can I use? I just said that in water resources assessment, the law of physics apply. It's a fluid mechanics problem, and I said in particular conservation of mass and conservation of energy. So an idea, or to be rigorous, conservation of momentum, which is a vectorial quantity. Energy, it's related to momentum, but it's a scalar. So to be rigorous, one should say conservation of momentum, which also implies conservation of energy under certain assumptions. So I need to introduce a second equation that is conservation of momentum energy. Given that we are not interested in describing water direction, the direction of the river flow, we can rely on conservation of energy. Another solution, if we don't want to use a physical law, because for some reason we don't like it, sometimes physical laws are complicated, another solution may be to introduce an empirical equation. Empirical equation means an equation that establishes on empirical basis a relationship between the two unknowns that I have here. The two unknowns again are river flow and storage W, river flow Q and storage W. So I have to introduce a second equation that is a relationship between storage and river flow. It can be energy equation, or it can be empirical. So let's see what is the solution that I am suggesting, not me, the linear reservoir is suggesting. It is this solution. Let me increase the size. Now, you see here a relationship between W and Q, which is what we are looking for. This is presented in the linear reservoir as an empirical relationship. It is precisely a linear relationship. It's linear. A good question is this empirical relationship also reliable? Also, let's say, appealing from a physical point of view? What is in a reservoir, in a tank, because here the catchment is assimilated to a tank. What is in a tank? The relationship, the physical relationship between storage and outflow. It is Torricelli's law, and which is precisely a conservation of energy. Let me look on the web. Oops, 1 second. Torricelli's law, Wikipedia. Here is Torricelli's law. I'm not interested in the derivation, but let me see if there is an expression, a simple expression. Here it is. Just 1 second. This is probably an image, yeah, but I cannot. Okay, I think you can see it. This is Torricelli's law, and Torricelli's law relates the velocity of the of the flow from a hole in a tank to the water level into the tank. Let me go back to the previous page. Because there is a figure that is interesting here. You see that there is a tank, which is our catchment, with holes, and the Torricelli's law gives the velocity of the flow through these holes depending on the water level above the hole. And you see it's highlighted here. Let me see. Yes, I can highlight it. 1 second. Let's wait for my highlight. So again, velocity V is equal to the square root of 2g. G is gravity multiplied by h, water level above the hole. Now, the water level is a proxy for storage, because if you know the geometry of your tank, you can substitute the water level with volume. So Torricelli's laws suggests, you don't need to learn it and to remember it, but suggests that the river flow, or the flow from a hole in the tank, V, it's velocity actually, but the velocity is linearly proportional to flow. We are not now going into the demonstration of this, just keep it for true. Velocity is linearly proportional to flow, which means Torricelli's law that flow is not linearly proportional to storage, is not linearly proportional to h, water level, and therefore not linearly proportional to storage. So physical evidence suggests that the relationship between W and Q is non-linear. I'm not sure you remember the definition of a linear relationship. If you don't remember it, please have a look. Allow me to open another web page. Before I open, remember the conclusion from this web page on the Torricelli's law. From a physical point of view, the relationship between storage and river flow is non-linear. Okay, now let's see the definition of a linear function, Wikipedia. A linear function, first of all, if you look at a graph, it's expressed by a straight line. But the definition of linear function is that you see here. 1 second. Let's wait for the display. Perfect. Two relationship, look on the left. If a function f is linear, then two conditions apply. F of x plus y is equal to fx plus fy. This is the superimposition principle that you as an engineer for sure already know. The second condition is f of a times x is equal to a times fx. This is a definition of a linear function. It is something that I may ask at the exam. Please remember it. As an engineer, you have to get extremely clear the meaning of linear and non-linear phenomena, process, function. If I say that rainfall runoff, it's a non-linear process, you have to be clear what it means. Okay? Now, let me go back to the linear reservoir. This relationship here, it's linear, while physics suggests that it's non-linear. Is this approximation acceptable? Yes, it is. It is for the purpose of simpler modeling. It's an approximation. It's an approximation which may be more valid under certain conditions with respect to other conditions. In general, there is a valid reason for using it in its linear form, and the valid reason is precisely simplicity. Today, simplicity is something that we don't consider important because we have a lot of computational power available. So we are not concerned by complicated analytics today because we can resolve complicated computations numerically. Actually, in the past, they were concerned by analytical complexity, and this is why they preferred the use of linear models. And this is why the linear reservoir was proposed in this form. Very good. So this is the kind of relationship we have, we needed, a relationship between W and Q. It is presented as an empirical relationship. On the other hand, we see that there is some physical connection. If we accept an approximation, we see that there is a physical connection. Very good. So let me go back to my web page. Now we have these two equations which allow us to solve the problem. Of course, you see that one of them is a differential equation. This is quite typical in fluid mechanics. conservation equations are frequently expressed as differential equations. Usually we get a bit concerned as engineers when we see differential equations, and we don't have to be concerned, actually. We absolutely don't have to be concerned, because a differential equation is nothing else than an equation that, instead of describing the variable, describes the increments of the variables. Given that we are interested in knowing instead the variable, this means that we have, once we know the increments, we have to sum them to get the value of the variable. It's nothing else than a summation that we need. And this is called the integral of the differential equation. This is another term that always scares us. Oh my God, the integral is difficult to compute. No, absolutely, it's a summation. It's difficult maybe to compute analytically, but if we compute it numerically, it's just a summation. So of course, by looking at these equations, I know that there will be an integral to compute, but I don't have to be concerned. And look, in order to get to the value of the variable, what I need is not just a summation. It's a summation which has to be extended to the initial and boundary condition. The initial and boundary conditions are the starting point of the summation. Initial conditions refer to time. Boundary conditions refer to space. Given that here I have only time as an independent variable, what I will need at the end of the story is an initial condition in order to compute my summation. Now, the next step is to resolve this system, therefore computing the summation, meaning the integral. But now we need a break. I need a coffee made in my house, of course. I cannot go out. And I give you, before making the break, a minute for questions. And look, after the break, now it's optional. After the break, I want questions from you, okay? This is compulsory. If you don't ask at least 2 questions, you can discuss on the chat during the break who is asking them. I am leaving the PC, so I'm not looking at the chat. And or you may discuss with the mic. I'm leaving the PC. If you don't get at least 2 questions, I don't restart lecturing, which is not, I mean, a big threat, but still, it's what I can do in these conditions. Because in physical presence, I usually identify the person myself if there are no volunteers. But in this case, let's try like that. So 1 minute for questions. Not compulsory ones. Yes, when we talk, so the question is, I didn't get this last part. Initial conditions refer to time and boundary to space. Yes, when we talk about integrating a differential equation, in general, we talk about initial and boundary condition. And we need these conditions in order to get a starting variable, a starting value for the variable. And then by integration, we add to the starting value the increments. But you know, we need the starting value. If we don't sum the increment, if we just sum the increments, we don't get to the value of the variable. We need an initial value, and then we talk about initial conditions. Initial means time. as the word suggests, beginning in time. And we talk about boundary condition. Boundary refers to space when we want to mean the starting point in space. But in this case, we don't need boundary conditions. We only have time here. There is another question. Can we get an idea of the graphic representation of this relation? You know, for the second one, WT is equal to K times Q. This is a straight line. The first one is still differential. We will get the graphical representation after integration. We will get the graphical representation later on. In the second part of the lecture, I want to integrate it, and actually I really would like to make the integration on a sheet, but I need to check whether I can use the phone to look at my sheet while I'm writing. I'm not sure about that, but we will try. It may take some time to make the experiment. I miss the blackboard, so I just want to find a way. Okay, let's take a break, 15 minutes. Thank you very much.